20 minutes even.
Yeah, this is probably enough.
Great.
Usually I talk too much, but today I will be talking little.
You okay?
Yes.
Okay.
Yeah. Okay. I talk. Yeah. So it's with great pleasure to be here at the 50th jubilee of Yakir's path-breaking and revolutionary work with his advisor, late David Bohm. It's a great pleasure. As I say, especially that I will be talking about relatively old stuff, as far as I'm concerned, because before I met first Yakir, of course, I had to familiarize myself with a problem, with the area of problems, you know, Dirac, magnetic monopole, fiber bundles. He discovered fiber bundles and so on. But when you actually remove the ball, the monopole, what is left is basically a string, is a fluxon. And so I basically always remove the things which are irrelevant and focus on the thing which is simple. Because I believe that everybody can compute. So now, so my title is not very original, because I mentioned already that people already thought about so-called Aharonov-Bohm medium, which is a name invented by Nambu for explanation of a confinement in quantum chromodynamics, in the theory of hadronic matter. And so, of course, it should not be surprising that, of course, I thought that perhaps Aharonov-Bohm medium is relevant for the structure and properties of quantum gravitational vacuum, the ground state. So it's a long story, I mean, as far as my evolution of my thought. And so the next statements are actually encapsulating of a long period of thought, gestation. So I think that gravitation, I came to the conclusion that gravitation is a phenomenon which is basically quantum mechanics in a macroscopic regime, which is basically saying something like quantum mechanics on the scale of 10 to 28 centimeters. And today I will finish the talk, if I get there, by proposing actually certain observations, measurements, which will be basically testing quantum mechanics, quantum coherence on the scale of a galactic scale. Actually, I communicated this to Yakir last summer. It is a little bit funny. What is funny? Let's see. Funny is that I don't know how to use these computers. You will see that I don't know how to use computers. Which button I push? This one. Yeah, because I became a Macintosh man. Okay, so now I know. Okay, so now Aharonov-Bohm effect and the whole area of Aharonov-Bohm effect and gravitational AB phenomena. When I use plural, I mean there are plenty of things which are there, and all of this is connected with AB. So first of all, let me show you how I was wrong all the time, for a long time, when I thought about this problem of what is called spinning cosmic strings. The name itself is a marketing, shows that in '86 I already knew how to do marketing in America. Namely, I had basically idea that there is a gravitational vortex, like a vortex in superfluid helium, or Ablyazov vortex, or Yakir's solenoid, but I had to sell it to these guys who are, you know, reading papers, reviewers, you know, referees. If you don't have a sexy title, they wouldn't publish a paper in physical review letters, you know. So this is why I call this a spinning cosmic string, you know, because at that time they have seen them in the sky, you know. Zurek Burek has reported, and so on. So so now, but you see, quantized vortices are very, very important. I think that all of you know the tale of a three or four men, as told by Richard Feynman, namely the importance of being earnest, namely how men understand quantum mechanics in application to the macroscopic systems. Superfluid helium is an example. It starts with Tisha, actually London, Tisha Lev Weidman, excuse me, Lev Davidovich, Lev Davidovich Landau, and of course Richard Feynman. The moral of the story is the following: if you measure and you discover vortices, this way you prove with your naked eye, without Brownian motion or critical opalescence, that there are atoms. You see, if you discover a vortex, you measure it with circulation, then you find out that actually there is a quanta of mass. So this is how I understood what actually Feynman did. And then I, of course, thought that maybe if we found such a Aharonov-Bohm, gravitational Aharonov-Bohm vortices in nature, in space, whatever, but not cosmic strings, God save, then it would be interesting to figure out the same way Feynman, Onsager-Feynman quantization condition. You see, you have a vorticity, or what is called fluxon, AB flux. You measure it, you find it, because it is macroscopic. It could be, the string could be as fat like this one, you see, the cross-section. I can tell you that it could be as big as this one. Actually, the biggest ones have a size around 10 to minus 3 millimeters, and it happens, or 10 to minus 2 centimeters, 10 to minus 2 centimeters, which happens to be a scale of dark energy. Okay, this is the biggest one, a fat vortex, I call it. So, okay, I will talk about for a few minutes about prehistory, which means before I made Yakir, and then this is, of course, after Yakir and after Kasher, of course, because you cannot, how to say. Oh, you see, here it is. Okay, in '92, when this first summer when Summer Institute at USC, University of South Carolina, we had this beautiful Summer Institute with all friends and very bright people who are coming. And now the place is so dull, you know. So I had this remarkable all-night discussions with Aaron, and I consider myself, in some sense, a student, meaning of both Yakir and Aaron, because how to put it, intuitive physics and quick discussions pointing out in different directions is important. So what you see here will be actually pictures. Now, when I say that by 95, 96, I have more or less figured out along these lines of Feynman logic of how you can figure out that if you discover a quantized vortices, if you are lucky in the measurements, then you could argue that there are constituents. Okay? Analog of the atoms of helium-4, these heavy particles would condense and produce a certain condensate. Condensate is a medium. Macroscopic quantum medium has vacuum energy. It has a tension, all kind of stuff, cosmological constant. So, but then there is a problem that everybody goes after the graviton. But I think the graviton, as Sidney Coleman would call it, is a red herring. It's completely irrelevant. It emerges. I would say that the first consideration is to go to the Coulombic or Newtonian sector in gravity, like in QED. And of course, because of relativity and causality, you get photons because of retardation effects. So if you, and this is actually, Aaron is nodding, actually he explained it to me. Okay? So, of course, I earlier knew that it is important to study stationary, axisymmetric, gravitational fields, because this is the way I derived Einstein equations. Okay? I mean, this is called Ernst equation, whatever, sigma model. So there is a way to derive Einstein equations by studying only stationary gravitational fields. So you say completely, you ignore gravitons. These are basically like photons, there's dissipation in the system. Dissipation comes because of relativity. So you study the static case. In the gravity case, you study the case of when you have a gravimagnetic field, because you have Coriolis forces, and you have Newtonian ones. But now, because everything gravitates, every energy gravitates, you have a coupling. You have nonlinear sigma model. So the question is, can you derive the nonlinear sigma model using arguments of a type of Einstein? Of course you can. The rest is mathematics. So you can derive then, by the argument of Aaron Kasher, you can derive Einstein equations and gravitons. So therefore, my conclusion was, I better first understand the AB character of Einstein equations, meaning stationary, axisymmetric, rotating gravitational fields. No, but they are nonlinear equations. How do you get nonlinear equations? Oh, yes. You have a non-trivial medium. It is Aharonov-Bohm medium. How would you do? You take a bunch of vortices, you do the coarse graining. The problem has a so-called coherence length, but you do the same thing what Feynman did for the, Newton bucket in the Feynman version. Namely, you take a superfluid bucket and rotate it. And what do you see? You see meniscus. You see a bunch of vortices. So how do you produce the effective velocity field in such a situation? You sum over all vortices, and you introduce the concept of average magnetic field. The same thing, you get average rotation. So you see what happens when you discuss discrete objects. The velocity is purely gradient, but the same thing is with matter. You have point particles, localized masses. When you introduce the concept of density, you are putting mass where it is not there. Therefore, when you couple it to Einstein, by, say, Newton-Poisson equation, you obtain unphysical fields, gravitational fields, potentials, because you put them where there's nothing. Anyway, I am, of course, of course, I finish almost, of course, but I'm only here. So, well, because, okay, so gravitational vortices was a beginning. In the gravitational vortices, which is the spinning cosmic string, what you find, I have these transparencies there, but this is just really irrelevant. I have to tell you what it is. You find out the pathology in the simplest possible case. Namely, you find a time machine, closed time-like loops. Now you see, people are talking about the, travel in time and so on, it's science fiction. Of course, it's clear that it doesn't happen because quantum mechanics forbids it. And I want to show you how I understood that this doesn't happen. You see, the gravitational vortex, the spinning cosmic string, is basically a tube which has some size. Inside, you would have closed time-lag loops. But I argue on the following way. You see, in the region outside, you have causality. Einstein equations are partial differential equations of hyperbolic type. Generic class of solutions is such that it's non-analytic. You have to allow the presence of shock waves and discontinuities. So therefore, the usual naive thing about Kruskal extension for black holes and so on, already you see in the case of this vortex. Now, I'll talk about apt analogies. Forget about this. This is just this statement here about black holes and the de Sitter space. It is the second part which you need to get to the conclusion that gravitation is a quantum many-body problem. Bioheuresis, okay? But anyway, the thing is that you can get the analogy with superconductors, the Onsager-Feynman vortices, very simply, by electromagnetic analogy. But this is all kind of funny thing, okay? So I don't want to bore you with the formula everybody should know or knows. It's basically a Cartan structural equation. Forms. These are the things you learn when you are 20 or something and later want to forget because it's mathematics. Okay, and you see here the flux. You see this one here, this little thing here, A. I did not know Yakir, but somehow I call this A all the time. This is. It's in my paper from 86 or 77, I don't know. But this is what is called torsion flux. You see, there was extension of gravity by Elie Cartan and many people later on, and what these people are talking about really is something like this. This is the same thing as the spontaneous symmetry breaking, and you have so-called unbroken phase. Broken phase, spontaneous symmetry breaking, and unbroken phase. Inside the vortex, the phase is unbroken. So in gravity, you have a picture, namely, you violate one of the conditions, namely that left-hand side there of a T, torsion, is not zero, but you want to do this in a minimal way on the wires, on the Aharonov-Bohm vortices. Okay? This is exactly the Meissner-Ochsenfeld effect. Okay? The torsion is confined. The flux is confined. Okay, now, that's the mathematics, but I have not finished the general picture, which is the following. Every mathematician knows, and this is sheer mathematics, that partial differential equations of hyperbolic type, or the one with I, h bar, hyperbolic, have a property that general solution is not analytic. So I always wondered why people would analytically continue through the event horizon of a black hole. It's a dangerous thing to do, a very dangerous proposition. So therefore, I consider the simplest case where I see this thing. And the pathology which appears here is called, you will see it immediately, because it's not expanded. I have it somewhere expanded. This guy combines with this, and you see there is R squared. R is a polar, is a cylindrical coordinate system. Z here, R and phi. So you see that if R is less than the modulus of A, this sign, the minus sign means it is space. But when this thing is R squared is smaller than A squared, it becomes plus. It's a time-like thing. But phi is a azimuthal angle. So you have a closed time-like loops. You have a time machine. Okay. In a nutshell, the most primitive case. So you see what I did is I basically did the complete surgery. I stripped completely the whole rotating systems into the wires. Because everybody knows that if I superpose AB vortices, cylinders, I get average magnetic field by a procedure called coarse graining. Okay? Like we do for densities. So this is this abomination, time machine, and so on. And it shows immediately that the region when R is equal modulus of A is a region through which you cannot analytically continue. So this metric is not valid for R less than modulus of A. Simple. But Einstein gravity doesn't, equations don't know it. Right? I mean, everybody can write a metric like this and see immediately what you see here. This is basically D of something, but be careful because you don't mix one compact variable time and a compact variable. Okay? You never mix. This coordinate transformation, if you call this C times dt prime, is an improper gauge transformation of the same type like you would try to, as you would try to gauge away Aharonov-Bohm potential. And dispose completely of the solenoid of vortex. So exactly on the axis, R equals 0, there is a strange guy. Is a vortex. And this is the same one as we have because of, case in the superconductivity, in superfluid helium-4, and the Yakir's cylinder. One message we have is this guy supposedly has no size. First of all, when in Einstein gravity, you have only G and C, you don't have H bar naively. So therefore, any interface you have, I'm finished almost. Any interface you have, this is wrong. Torsion is completely irrelevant. This is the analogy, apt analogy I was talking about a long time ago, but I really want to go to this. You see, you had the gravity case. The basic equation was first that torsion is 0, but torsion was covariant derivative of order parameter, which here is a psi complex in Ginzburg-Landau picture for superconductors, or Ginzburg-Pytajewski for superfluids, and phenomenological description. And there you have E. It's kind of vectorial object. But on the other hand, you see this analogy, we call apt, if it captures something. You see, in gravity, the analog of electric charge is the mass. But because of relativity, a mass, energy, is the component of the 4 vector. This is why this TA, this flux, is a kind of internal 4 vector. So you see, everybody can compute. So therefore, I only show you this is the explanation. Oh, this is the scattering cross-section. By the way, this shows that I cannot compute. Because I ignore completely mixed term. You know, there's some mixed term here, you know, just... first of all, the reason is very simple. You are basically conical. You know, when you go on a cone, you are basically, you know, meeting the problem of a cone heads, like in this movie. So basically, it's a problem, and you make a mistake, and there is another term. But I say, take alpha to be 1, then you have basically thing going from the right to the left, so there's a cosine squared of theta half, and here is a famous periodicity, and notice that this thing here, 4gj, multiplies energy. But this 4gj is, you know, this stupid interpretation that is something like under momentum or torsion, flux, whatever. It is none. It is A. And this comes next. This is it. Okay? This A, I told you before, I don't care that I can write this as a 4gj because this is a red herring. I'm looking at splitting, you know, a hair. A, writing as a 4gj and thinking about, oh my, J, what is this meaning? Dimensionality is under momentum per unit length. And then, of course, I get the wrong picture about this, you know, torsion. So now the Aharonov-Bohm periodicity is there. The analogy of superfluidity appears naturally. And here you have a beautiful, I think that the rest is history. I wanted to tell you basically this. AE, Aharonov times Einstein, is equal h bar n, where n is integer. And now here comes Berry. Okay, how Berry comes into the picture? Well, what you do is the following. It's relativity, you have a heavy particle. You know, the result of quantization is independent of velocity of particles. So E can be m c squared. Okay, so therefore what you have is this formula really is the same as the left-hand side, and this you recognize as the Onsager-Feynman. So therefore the moral of the story is the following. The A is actually related to a quantum of vorticity, which is hidden in the vacuum structure of gravity, and the so-called spinning string gravitational vortex is a slight deformation, a defect in a vacuum. A vacuum has lowest energy. Of course it must be flat then, right? So this metric was locally flat, except this vortex. So on the side of a condensate picture of a vacuum state for gravity, this is a state which is homogeneous, completely, you know, tranquil, spokojny, tranquil. And somewhere a vortex appears, and this produces slight disturbance. And that is a non-integrable phase. And then you see, you have this beautiful thing. Namely, I read now, you see this what is, I read from, you see, quantization, Dirac quantization can be read from right to left. By this I mean, I first look for the vorticity, quantized vorticity. I see them with naked eye in liquid helium-4. And then, from this I conclude that there is a strange thing which has a dimension of mass, and voila, well, this must be some kind of quanta of mass. Atoms, helium atoms here, gravitational atoms, I call them gravitational atoms. They are still hypothetical, but I hope to see them. And where you see them is the last transparency, but I can tell you in words. Sagittarius A star, 4 million solar masses black hole, is now mapped by astronomers in a very long baseline thing. And what you have to do is basically a simple thing. If there are gravitational atoms, and the vacuum state is a condensate, is like superfluid, what is a black hole? Black hole is a bubble of superfluid bubble which rotates, gets deformed, but it is, you know, inside plenty of vortices. You understand? And vortices make things. Professor Zonin is now going to be thinking that I don't know anything about vortices because he spent most of his career, I mean, plenty of career to study the vortices, but I have learned belatedly, okay, because I was little when they did the experiment. The analog of the Meissner-Ochsenfeld expulsion of magnetic field was measured only in the late 60s in the Weaver and Fairbank experiment, meaning the non-classical moment of inertia. So I'm telling you simply that what I propose is to do the most giant measurement of the type of Fairbank and Weaver by observing the stuff which is the closest, biggest black hole for us, which is 4 million solar masses. And how do you do this? You measure the moment of inertia. How do you measure? I have to have J and M, right? Once I measure these two guys, then I find out what the moment of inertia is. If the moment of inertia is much, much smaller than the classical Einstein theory, you know, for Kerr black hole, everybody can compute. I have not seen it, by the way, but you know, you can compute it. Anyways, that's all. That's all.
Thank you.
Yeah. This is this formula. So in my abstract, I say that I propose to find out if Aharonov is right macroscopically.
You can tell us all about it over coffee.
Okay, of course. Anyway, do you see you know, I feel that